Hi. Um, I'm gonna be honest. I kind of forgot that the channel existed, and then, yeah, my friend reminded me, "Hey, what about your channel?" And I'm like, "My channel? Oh yeah, my channel." So yeah, I'm still alive. Well, kind of. I'm currently a little bit kind of sick, but it's okay because tomorrow we have a test. What test is it? I hear you asking, ladies and gentlemen. I give to you electrostatics. Wow, electrostatics! We're finally playing with electricity. I'll be honest, this might be one of the harder ones, but yeah, it's all right. Okay, so electrostatics. What does that mean? Electro meaning like electricity, and statics meaning like not moving. So the electricity is not moving. Oh, that's fair. That makes sense. So what do we have in electrostatics? One of the most important things that we have in electrostatics, then the thing that you need to understand, is that we have charged particles and objects. What the hell do I mean by charged particles and objects? I mean that everything can be charged. What does charged mean? What does charge mean? Well, let's look here. Charge. There's two types of charges. There are positive charges. There are negative charges. And if we remember the atomic structure, oh my goodness, so cool. We have like the nucleus here, and then we have like the electrons roaming around it, right? Now, these electrons are negatively charged, and the nucleus has this thing called a proton. This proton is positively charged. Now, an object or something, not really particle, but an object is called positively charged when it's lacking electrons, and it's negatively charged when it's um, plenty in electrons. Basically, a lot of electrons and not much electrons. But how can there be an imbalance of electrons? Well, one of the ways that we can, transfer electrons is by rubbing. Rubbing. You can rub stuff with different materials to somehow make the electrons move. I don't know. I don't know how. This has some chemistry stuff. I don't get it, but you can do rubbing to make electrons move from one, let's say here. It's like there's two, and there's like only one here. Actually, wait, let's say there's two here. And then you rub them against each other, and then it can end up like this. One, two, three. Like it moves here, it moves there. Making this lacking in electrons, or positively charged, and this one plenty in electrons, making this negatively charged. So remember, the thing that is moving is the electrons. The electrons are moving, not the protons, not the neutrons, but the electrons. Okay? Okay. Now, these are called the charges. 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 Whoa, charges. Now, one electron has a charge of 1.6 times 10 to the power of negative 19 coulomb. Coulomb is the unit for a charge. All right, it's coulomb. That's the standard. That's coulomb. Coulomb. All right. Very cool. Now, what can happen? What are the interactions? What can happen between these charges? Well, okay, hold on. Let me check my notes. That's my chair, by the way. I'm not farting. I swear. Okay. Let's see. Okay, first, let's represent the object by just one point to make things easier. Later in the video, I will be covering more real objects like plates and spheres. Cool, cool. Okay, for now, let's just stick with like circles. Nice. Okay, now let's say we have a circle a point with a positive charge and another point with a positive charge. Now, a really smart guy named Coulomb found that there are interactions between charges, and it's really similar to gravity. A rule to keep in mind is if it's the same, they repel. If it's different, it's this. It's attract. They attract. Yes. Brain fart a little bit. Okay, sorry. Okay, so let's look at this case again. Two positively charged points. It's the same, right? So what will they do? They will repel. What does repelling mean? They will like get away from each other, if you want to imagine it like that. They will run. They will run away. So boom, they will repel. But how? What makes them repel? What makes them get attracted? These are caused by a force. The force, as Coulomb has discovered, is defined as K, Q, Q1. I'm going to call Q1, Q2 over R squared. All right. What the hell are these things? Okay. Q1 is how charged is the first point, and Q2 is how charged the second point is. So it could be like 2 coulombs and 3 coulombs, 7 microcoulombs and 6 microcoulombs. It could be negative 2 coulombs and positive 200 microcoulombs or something. Yeah, that's the Q's. The R is the distance between the charges. That's R. Remember, it's squared, R squared. Alright, cool. It's squared, R squared, remember. And K here is a constant, where K is defined as 9 times 10 to the power of 9 Newton meters squared per coulomb squared. Don't mind the unit, it's just there, but just remember this number, 9 times 10 to the power of 9. Cool, cool. Alright, so we know. Wait, I'm gonna draw F here. It's like, yeah, the force is pushing away, pushing away. Two positive charges, they push away. Alright, now pop quiz. Real quick pop quiz. What if I have two negative charges? What will happen? Will they push away? Will they pull each other? Well, let's look at the rule again. If it's the same, they will repel. If it's different, they will attract. So, this is a negative one. This is also a negative one. They're both negative. I don't know why I did that. Uh, they're both negative. So it's the same. And because they're the same, they will repel. Very easy. Boom. Boom. See? Not so bad. Alright, let's do another one. This is going to be an easy one. What if I have a positive and a negative this time? Ooh, this is interesting. They're different this time. They're different because one is positive, one is negative. So now they're going to attract. They will pull each other closer. Aw, they're so cute. Oh, wait, that's a really weird line. Boom. Boom. They'll pull each other closer. So romantic. Oh my god, so cute. Okay, see, quite easy. Let's do a quick recap. So charges, we have things, charged particles, and we can make something more charged, more negatively charged by rubbing it, and the electrons will move. And there are interactions between the charges. One of them is forces acting on them. The forces appear because, well, they're charged. And the magnitude of that force is equals to this equation right here, K multiplied by Q1 Q2 R squared, where K is equals to 9 times 10 to the power of 9. Q1 is equals to how charged, I guess, how charged the first particle is, and Q2 is how charged the second particle is, and R is defined as the distance between the two. Remember, standard units. Remember the standard units. R is in meters, and Q is in coulombs. Alright, cool. And a rule of thumb for determining the direction of the forces, if it's the same, they will point away from each other, like so. They will point away from each other. But if it's different, if it's a positive and a negative, they will point towards each other. They will attract, like so. All right, cool, very nice recap. Let's do some practice questions. Very easy ones. Let's see. Let's say we have particle here and then particle here. What the freak? I think my screen's dirty. Hold on. Let me just and particle here. Okay. Let's say the distance is equals to 1 centimeter. Let's call this Q1. Let's call this Q2. We know that Q1 has the charge of 2 microcoulombs, and Q2 has a charge of 3 microcoulombs. The question is, what is the force experienced by particle 1? What is the force experienced by particle 1? All right, cool. Let's think about this. Let's write down what we know first. What do we know? We know the distance between the particles. What is that? That is r here. This is the distance. So let's write that down. R is equals to 1 centimeter. But oh wait, remember, we need to do everything in standard units. This is centimeter. We need to convert it to meters. So we need to divide it by 100. You can rewrite this as 1 times 10 to the power of negative 2 meters. All right, cool. What else do we know? We know Q1 and Q2. The first one has a charge of 2 microcoulombs. Now, to convert microcoulombs to coulombs, you need to divide by 10 to the power of negative 6. So this is equal to 2 times 10 to the power of negative 6 coulomb. And we know Q2 is equal to 3 microcoulombs. Equals to 3 times 10 to the power of negative 6 coulombs. And we have everything. Like, I'll give you a few minutes to try and solve it. I'm gonna grab some water. I'll give you guys a few minutes to solve it. I'm gonna grab the water. Water. You guys done? I'm back with the water. Okay. Let's solve it together now. The answer is da 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 da. I don't know. I can't do it in my head. Alright, let's just try and solve it now. So we need to find f. We know f is equals to k multiplied by k1 multiplied by k2 divided by r squared. We have everything. K, that's a constant. We know that. Q1, we have that. Q2, we have that. R squared, we don't have r squared, but we do have r. So we have everything. So let's just plug in the numbers. K is defined as 9 times 10 to the power of 9. Q1 is 2 times 10 to the power of negative 6. Remember, we need standards. We don't put in 2 because that's in microcoulombs. We want coulombs. And 2 microcoulombs is equal to 2 times 10 to the power of negative 6. So this is 2 times 10 to the power of negative 6 multiplied by 3 times 10 to the power of negative 6 divided by r squared. So that's 10 negative 2 to the power of 2. Let's just rewrite everything again. 10 to the power of 9, 2, 10 to the power of negative 6, 3, 10 to the power of negative 6 divided by 10 to the power of negative 4. Okay. Let's work on the power of tens. This has a power of 9. This has a power of negative 6. This is negative 6. So we can add these up. So these becomes negative 12. And you can add these up to make the sum into 10 to the power of negative 3. Is the math right? Yeah. And now we're going to divide negative 3 here by negative 4. So negative 3 minus negative 4 will equal to 1. So the resultant here will be 9 times 2 times 3 times 10 to the power of 1. That's how you work out the powers of 10. Now 9 times 2, 18. 18 times 3, that's 540. So the answer is 540 newtons. Very easy, very nice. Oh my god. Okay. Let's do one more question. I feel like we can do one more question. Hold on, let's see. That's magnets. Wait, is it? No, not magnets. Okay, let's do one more question. Hold on. Uh, Ooh, this is a very nice question. Okay, let's try this one. So imagine we have three charges now. Ooh, we're immediately leveling up. We went from 2 to 3. Amazing. Imagine we have three charges. We can call this 1, 2, 3. All right, cool. Now let's say the distance between here to here is equals to 1 centimeter, and the distance here is equals to x. Very nice. Okay. Now we know the things that we know. Q2 has a charge of negative 1 microcoulomb. Q3 has a charge of 16 microcoulombs. And Q1 has a charge of 10 to the power of negative 2 microcoulombs. And now we know. And we know that this first charge is not moving. Or in other words, it's in equilibrium. I think that's how you spell it. Equilibrium. Yeah, it's not moving, or it's in equilibrium. So now the question is, what is distance x? I'll give you guys a minute to figure it out. Oh wait, I just realized. I forgot to ask. What is the direction of the force here? Wait, let's go back really quick. What is the direction of the force? Really quickly. This is 2 microcoulombs. This is 3 microcoulombs. They're both positive. Okay, they're both positive, which means they're the same. Which means they will repel. So repelling would go. The force would go like this. So the force acting on particle 1 will go to the left. It's going to the left. All right, cool. All right. Good luck, guys. I'll give you guys like 3 minutes, I guess. Yeah, 3 minutes. Sure. I'm gonna try to find some other questions. God bless water, bro. I love water. Water's so good. Although I do have a book here, just the book of knowledge, I guess, and it has a lot of questions. This question I got from the book. I think let's try doing all of it in this video because it's fun. Why not? Okay, so in that case, I'll give you guys the options. The options is A. While you guys are still doing it, the option is A, 1 centimeter, B, 2 centimeter, C, 3 centimeter, D, 4 centimeter, and E, 5 centimeters. All right, 2 minutes left. Let's go. Oh my god, I love drinking water. Drinking water. Drinking water. Ooh, actually, I just thought of a really good question. I think it's all in my head. It's all in my head. Yeah, just a random question I thought of. Like, hey, it will be interesting. So yeah, do that later. But it's just number 8 on the book. I'll mark it's number 8 on the book. And that is time. It's like 2 minutes, but I got bored waiting. Okay, so let's think about this. What do we know? We know Q2, Q3, we know Q1, we know distance. Now we just need to find x. Alright, so let's convert everything into standard. So this will be -1 times 10 to the power of -6 coulombs. be 16 times 10 to the power of negative 6 coulomb. This will be equal to 10 to the power of negative 8 coulomb. Nice! And this will equal to 10 to the power of negative 2 meters. Alright, cool. So, what do we mean by not moving? Equilibrium, what is that? Remember, in I think 10th grade, 11th grade, I don't know, in dynamics, equilibrium means the resultant force is equals to 0. What does that mean? So, wait, hold on. I should write this down. I'm just talking to myself. Equilibrium means that resultant force is equals to 0, or sigma F is equals to 0. What does that mean? What the freak does that mean? So imagine you have multiple forces. Let's say we have this force, force 1, on an object, force 1, this is force 2, this is, and then there's like force 3 here. If we say the object is in equilibrium, that means if you add up all of these forces right here, if you add them up, it will equal to 0. But then again, we need to remember, these are vectors. We're working with vectors, so the direction matters. So, let's do the question now. We know object 1 is not moving. So, from that, we get the hint that we should probably be analyzing object 1. So, here, this is object 1. Okay, cool. Now, object 1 will experience some forces. What are the forces? Well, this force, the KQQ r squared. This force. But what's the direction? Let's give the ball some symbols to make it easier to visualize. We know Q1, this is positive. So Q1 is positively charged. Q2 is negative, so Q2 is negatively charged. And 3 is positive, so it's positively charged. Okay. Let's draw it now. So, Q1, the first one will have interactions with the second one. What are the interactions? First one is positive, second one is negative. They're different. What does it mean if they're different? If they're different, that means they're gonna attract each other. That means the force will go this way towards the second object. So it's gonna be like this. Let's write this as F experienced by object 1 caused by object 2. Alright, cool. Now let's look at the third object. Even though it looks far, it still has some interactions. Now, 1 is positive, 3 is positive. They're the same, so they're gonna repel, they're gonna push away each other, which means it's gonna go that way, it's gonna go to the left. So if we draw it, it's gonna go here. Boom. Or, oh yeah, I gotta sneeze, hold on. Alhamdulillah. Let's write this as force experienced by object 1 caused by object 3. Alright, cool. Now we have all of the forces. Now, if we add up the forces, it's going to equal to 0 because it's in equilibrium here. But we need to remember, vectors, right? They have direction. So the direction matters. So let's assume all the vectors pointing right is positive, which means the vectors pointing left is negative. So let's write the equation down. Sigma F, the sum of forces, will equal to 0. Forces pointing right will equal positive. This is pointing right. So this is going to be positive, and this is pointing left. So this is going to be negative. Now we add them up. Force caused by force experienced by object 1 caused by object 2, positive, remember? Minus force on object 1 caused by object 3 is equal to 0. Now if you you can also write it like this, or it's the same. Because they're like canceling each other out, I push you with 2 newtons and you push me back with 2 newtons. The resultant is going to be 0 because it's the same size. So we can say that the size of this is equal to the size of this. Remember, the size is the same. It's not exactly the same because the direction is different, but the size is the same. Okay, now let's write this in the equation form if you want to say that. So we know that K, Q1, Q2, remember, Q1 and Q2 divided by, let's call this the distance between object 1 and 2. Let's call this, let's call it R, because this is X, right? This is X, this is X, and this is R. Alright, cool. So the distance between object 1 and 2, it's r. And r is equals to this. This is r. So let's just write r. Just for now, is equals to k, q1 and q3 this time. Remember, q1, q3 divided by what is the distance between object 1 and object 3? Okay, hold on. This is really messy. Whoa. I'm gonna redraw it. Where do I redraw it? I'll redraw it here. Okay. So this is 1, this is 2, this is 3, this is r, this is x. What is the distance from here to here? Well, obviously it's just r plus x, right? Because we're adding them up here and here. R plus x. Okay, cool. So it's going to be r plus x squared. Okay, remember that. The distance is squared. It's not r squared plus x. No, no, no. That's wrong. Whoa. Hello, Vsauce. We're squaring the distance, not r itself. We're squaring the distance. So the x is going to get squared too. Now, simple algebra. We can cross this out. We can cross this out. So we'll get q2 over r squared is equals to q3 over r plus x squared. Now, a really good trick my teacher gave me is instead of making this into r squared plus x squared plus 2xr and then solve the square and then solve for x, working with powers of 2, it can be really difficult. So what my teacher did is making like this. You collect the powers of 2 on one side and the powers of 1 on the other side. So we can move this here and we'll move this down. So we'll get r plus x squared over r squared is equals to q3 over q2. Now, by properties of exponents, we can rewrite this as r plus x over r squared is equals to q3 over q2. Now we can root both sides and we'll get r plus x over r is equals to q3 over q2 roots. Alright, now let's plug in the numbers and solve for x. So where is it? R is equal to 10 to the power of negative 2. I'm going to write it here. There's so much empty space here. I'm going to write it here. 10 to the power of negative 2 plus x divided by 10 to the power of negative 2 is equals to the square root of q3 is equal to positive 16 times 10 to the power of negative 6. 16 times 10 to the power of negative 6 divided by q2, which is equals to negative 10 to the power of negative 6. Okay, I forgot to mention, in these force problems, we're going to take the absolute value of the charges. Basically, if you're putting the numbers into the equation, you do not want to bring the negative sign. Don't bring the negative sign. Do not bring the negative sign. Just bring the number. So instead of putting in negative 10 to the power of negative 6, no. We'll just put in 10 to the power of negative 6. Okay, cool. And you can cross this out and we'll get 10 to the power of negative 2 plus x over 10 to the power of negative 2 is equals to the square root of 16. So 10 to the power of negative 2 plus x over 10 to the power of negative 2 is equals to 4. And then what? And then we'll have 10 to the power of negative 2 plus x is equals to 4 times 10 to the power of negative 2. And x is equals to 4 times 10 to the power of negative 2 minus 10 to the power of negative 2. Or it's equal to 3 times 10 to the power of negative 2 meters. And is 3 times 10 to the power of negative 2 in the options? Let's see. No. But we can convert this into centimeters by multiplying it by 10 to the power of 2. This is going to cross out. So we'll get x is equal to 3 centimeters. Is 3 centimeters on the board? Yes, sir. The answer is C. So x is equals to 3 centimeters. Alright. That's cool. Very nice. Not that bad, I think. Let's do another question. This is a question I made up. So, wait. Okay. Imagine we have 2 charges. I'm gonna put in some easy numbers because I can, but All right, we have two random charges. All right, actually no, not random. This is Q1. This is Q2. Okay, let's see. Let's say that Q1 is equals to I don't know, 2 coulombs. Q2 is equals to let's say let's say let's say let's say 2 coulombs too. Yeah, sure, why not? And let's say the distance between these two, let's call it R12. The distance between the two is, let's say, 1 meter. No conversions, really simple. But now, stay with me. We placed another charge. Let's call it Q3. We placed another charge somewhere. It could be here, it could be here, it could be here. But it's on the same x-axis. We placed a charge, a Q3, somewhere along this x-axis line. Let's say, I'm not gonna say anything. We don't know about anything. But one thing we do know is that this new charge that we placed somewhere here is in equilibrium. U3 is in equilibrium. Okay? Okay. Now the question is, what is the distance between Q1 and Q3? Alright? Think about it. I'll give you guys like, I don't know, I think 3 minutes is a good time. I don't want to wait 3 minutes. 30 seconds. 30 seconds. Good luck. How do you do this? Wait. Oh yeah, never mind. I got it. Yeah, remember Q1, 2 coulombs, Q2, 2 coulombs. The distance is 1 meter, and then we placed Q3 somewhere there. You know what? Let's Okay, I want to add one more thing. Q3 is a negative charge. Q3 is negative. Boom. I think you have everything that you need. All right. Find the distance between the first charge and the third charge that we randomly added. All right. Cool. Very nice. Man, being sick sucks, man. I hate being sick. Ugh. Ugh. Should I drink medicine? I can. Yes, I can. Let's keep going. All right, that's done. We're done. Okay, I'm ready again. I've mentally prepared myself. Okay, so how do we even start? How do we even begin to comprehend this question? Okay, let's think about this. Q3 is in equilibrium. That means the forces acting on Q3 is canceling each other out. Okay, yeah, that makes sense. Yeah, I already said that. And we know that Q3 is negative and Q1 and Q2 is positive. Okay, yeah, cool. So now what? Let's imagine 3 cases first. Actually, no. Actually, wait, yeah, let's imagine 3 cases. The first case, Q3 is to the left. The second case, Q3 is in the middle, and the third case, Q3 is on the right. Which one of these cases holds true that Q3 is in equilibrium? Okay, let's imagine the first one. Now we know Q3 is negatively charged, right? Okay, let's look at the first case. Wait, hold on. I'm gonna move it a little bit. Like right there. Yeah, okay. We know that Q3, if it was on the left, it will get pulled by Q1 and Q2 because, okay, let's recap again. This is Q3, 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 and then there's Q1. The force experienced by 3 caused by 1, where will it go? Which direction would go? It will go this way. It will attract. And then by 2, it's also positive. So it's going to attract 2. Now I ask you this. Is it possible for Q3 to be equilibrium in this position? 3, 2, 1. No, it is not possible. Why? Because the forces are in the same direction. They're not canceling each other out. Therefore, it's impossible for the object to be in equilibrium. So this case is impossible. And if you think about it, this case is also impossible because they're both pulling on each other. Yeah, they're both going the same direction. It's the same as the first case, but this time it goes to the left. It's impossible for the object to be in equilibrium because the forces are not canceling each other out. So this case is also impossible. So now we know that the object, the Q3, has to be between the first charge and the second charge, right here. Because, let's call this Q3. Now, Q3 will experience a force by 1 getting pulled like this, F31, and then by 2, F32. See, they're going different directions. That means it's possible for them to cancel each other out. Okay, that's cool. Now we determined where the position is, but now, what about the distance? Okay, we're gonna do some assumptions now. Alright, so let's draw it again in a cleaner fashion. This is positive, negative, positive. Let's say, because we're trying to find the distance between the first and the third one, let's say the distance between the first and the third one is x. So we're going to solve for x. Now, what about the distance from 3 to 2? Do we put x2? Well, no. It's not always equals to x. So, what do? Do we put another variable? We don't want to put more variables. So, what else do we know? We know the distance between the first one and the second one is equals to 1 meter, right? So, in that case, what if I say this is equals to 1 minus x? Well, yeah, duh. So imagine we have 1 meter. This is x. We cut this out. Boom. So it's just this. So it's 1 minus x. Okay, cool. Cool. Alright, so we have to determine the distances, and now let's just plug it in. Same as the previous problem, we will draw the direction of the forces first. F31 is this way, and F32 is this way. Now, let's assume to the right is positive, so to the left is negative. So this will be positive, this will be negative. So sigma F is equal to 0 because it's in equilibrium, and then F32 minus F31 will equal to 0, and F32 will equal to F31. Cool. Alright, now we write the long form equation, I guess. K, Q3, Q2 over the distance between 3 and 2. That is 1 minus x. Square it. K, Q3, Q1 divided by distance from 3 to 1. That is x. We're trying to find x. Okay, so we're going to cross out the k, cross out the q's, and we'll get Q2 over 1 minus x squared equals to Q1 of x squared. Remember the trick. We're going to isolate the squares. So we'll get x squared of 1 minus x squared, parentheses, is equal to Q1 over Q2. And then we square root. So we get x over 1 minus x is equals to the square root of Q1 over Q2. Let's plug the numbers in. Qx we don't know. Q1 and Q2 we do know. They're both 2. Alright? So x, 1 minus x equals to 2 divided by 2 and then rooted. 2 divided by 2, that's just 1. The square root of 1, that's 1. So x over 1 minus x is equal to 1, which means x is equal to 1 minus x. Why? Because we're multiplying it by 1 minus x. We're basically, we're moving it to the right. 1 minus x, and then you multiply by 1. Because, division turns into multiplication, multiplication into division, addition into subtraction, subtraction into the addition, And now we solve for x. We'll get 2x is equals to 1, and x is equals to 1 half. Or 0.5 meters. Or 50 centimeters. So the final answer that we get is the distance between object 1 and object 3 is equals to 50 centimeters directly in the middle. Now, the answer isn't always going to be directly in the middle, but this case it's directly in the middle because the charge from both particles has the exact same magnitude. It's the exact same size, exact same sign too, so it's directly in the middle. That's why it's directly in the middle. Alright, cool. 40 minutes and we're still talking about force stuff so much. It's okay, the grind never stops. Let us continue. Should we do another question? I want to do another question, low key. Okay, let's speed run through these easier questions. Alright, number 1. Two charges have a distance of r. Alright, cool. And then this causes a force. There's a force F caused by this. Yes. If the distance becomes twice as big, how will F change? Alright, cool. Let's think about this. Let's write down F K Q1 Q2. I forgot to write down R squared. Okay, cool. But then we changed it into 2R. So let's call it F new. It's equals to K Q1 Q2. Nothing changed, only R changed. So now this becomes 2R squared, which is equals to K Q1 Q2 over 4R squared. Oh, but wait a minute. K Q1 Q2. Oh, so the new force will be smaller by that much. The new force will be wait, what's the answer? Oh, okay. We're gonna multiply this by 100%. So we'll get the new force will be equal to the original force, but multiplied by 25%. So the answer is gonna be D, which is 25%. Alright, cool. This is a play on if this changed, what will change on the other one, It doesn't mostly rely on calculations, but mostly rely on equations. And a fast way to do this is to look at the equation K Q1 Q2 R squared and look at the positions. Let's rewrite this as F over 1 so it doesn't get too confusing. If it's on the same side, let's draw a line here. If it's on the same side, if one gets bigger, the other will get bigger. But if it's on opposite sides, if one gets bigger, the other gets smaller, alright? So let's say if Q1 gets bigger, what will happen to F? Well, of course, F will get bigger too. If Q2 gets bigger, F will get bigger too. But if R gets bigger, F will get smaller. Why? Because R is on the bottom side, but F is on the top side. They're on opposite sides. So if R gets bigger, the F gets smaller. This is about proportionality. Now, if you want to figure out how much they get bigger by, you look at the powers. If Q gets 2 times as big, then F will get 2 times as big too, because Q has a power of 1. But if R gets bigger by 2, then F will get smaller by 4. it will get smaller will mean divided by 4. If this becomes 2, why? Because it has a power of 2, and 2 squared is equals to 4, and that's why we divide it by 4. We look at the powers. That's a fast way to do this, and this is like a, I don't know, this is how I do it. Very concrete. Very hard to go make mistakes on this one. And this one is, yeah, fast if you need time. All right, move on to 3 charges, triangle, total F. What? Oh God, what is this? Oh dear. We have 3 charges on corners of a same equilateral. I don't know, same side triangle. Yes. If the forces between 2 charges is F, what is the total force? Okay, so that's easy, I think. Okay, so let's look at what we know. Same side triangle. Okay, the force between two of these particles is equal to F, and we know the particles are the same. Identical particles pushing away. All right. Repulsion. Very cool. All right. So now what do? We need to find the total force. Okay. I can do that. How do you do this? Okay. So, okay, I'm gonna pick one of these balls to analyze. I'm gonna pick this one. All right, because it's all the same charge, the same particle. It's gonna experience repulsion. The first one is gonna experience repulsion this way. Boom, F, because we know it's F from two. What am I saying? The force experienced by 2 charges is equal to F. Yes, and from this one is also gonna be F. Okay, wait, hold on. Big problem. We've been working in 1 dimension so far. We're just gonna add them up, positive, negative. But what about this? 2 dimensions. How do we add these vectors up? Well, we're gonna do a vector addition. If you have 2 vectors, let's call it vector A and B. The resultant of both of those vectors is equals to A squared plus B squared. I think it's minus. Or is it plus? Wait, hold on. Let me check. Is it plus? Wait. Oh, it's plus. Plus 2ab cosine theta. What is cosine theta? This is cosine theta. Okay. But be careful, ladies and gentlemen. Theta is the angle formed between 2 vectors when both of the vectors are pointing out from one point. If we have a point and the vector is going this way and the other is going this way, this is not theta. No. That's not theta, ladies and gentlemen. Why? Because one of the vectors are pointing inside instead of outside, and we don't want that. We want both of the vectors to point outside. So what do? We can actually draw the vector longer, right? So it was pointing this way, right? So let's just draw it longer. Boop. Okay, now they're both pointing outside, so this is theta. Okay, just keep that in mind. Okay, so now the question is, what is the size of theta? Oh dear God, how do we do that? We do it by this triangle. All right, cool. Same side triangle, even cooler. The total angles in a triangle is equal to 180. And because it's the same side triangle, all of the angles will be the same too. Let's call it theta. Yeah? Okay. Call it theta. If we add theta up, it will equal to 180. So theta plus theta plus theta, 180. 3 theta, 180. Theta, 60 degrees. So theta is 60 degrees. Alright? But this is different. This is different. We're looking at this. Not this. What? Well, actually, if we have 2 intersecting lines like this, if this is theta, this will always equals to theta. So across, it will be the same. This is fine. This is fine. Cool. Cool. Yo. So we know F, and we know theta. Let us continue. So resultant force will equal to F squared. Oh, sorry, the square root of F squared plus F squared plus 2F multiplied by F by cosine 60. So F squared plus F squared plus 2 F squared multiplied by cos 60 half. Pass this out. We got F squared plus F squared plus F squared is equal to. Why am I here? That's okay. Bro. Okay. Play Store. What the freak, man? There's no time to play. There's no time to play. Okay. Now let's add them up. We got 3F squared. Why does it say somewhere now? And then it's gonna be square root of 3 multiplied by square root of F squared. And this is square. Boom, boom. It's gone. Now it's F bar square root of 3. And that's the resultant of the first. It's D! Whoa! Very nice. Ooh, number 3. Let's see number 3. A graph that describes the connection between force, the Coulomb force, and the distance. Okay, well, I'm not really sure how to explain this because I don't know how to do this as well. Okay. So let's see. Okay, I'm really stuck on 2 choices, but I don't know which one is right. Is that logarithmic or is that exponential? Okay, hold on. So let's write the equation first. 2 squared. Okay. F on top, R is on the bottom. So if R gets bigger, if R goes to the right, then F will go smaller. So every graph that looks like this, or this, or this, or this, that will be wrong. That's a wrong graph because this would mean if R gets bigger, F will get bigger also. But that's just wrong! Oh my goodness, how could that be? Because, F is on the top, R is on the bottom, and like I said, if yeah, like I said. So I'm currently thinking if it's this. Looking at the options, there's this, and there is this. Now the thing is, they're both pointing down, but I think the correct option is equal to this. Why? Because, well, the way I'm thinking of it is if we have the graph like this, that would mean it's going to intersect here at one point. But here's the problem. How big R gets, it will never make F equal to 0. Well, intersection here would mean F equals to 0. And this is not possible. By only changing R, F will never equal to 0. So in this case, it's only gonna approach 0, but never actually reach 0. It's gonna get really close to 0. It's not gonna be equal to 0. It's gonna get really close to 0, but it's never gonna be 0. That's the thing. So I think this is the answer, and that is D. All right, very cool. I'm tired. I'm sick. I'm hungry. My cousin literally just asked me to eat. But guess what? I'm making a video. So I think that's it from forces. I hope everyone understands forces. Let's move on to the next one. You might be wondering, next one? It's been 1 hour. What do you mean next one? Yeah, there's the next one. Anyway, next we will talk about the electric field. Electric field. We just talked about some forces, and now we're going to talk about the electric field. What is the electric field? To use some slang, electric field is like an aura. How much aura a charged particle has. Now, if you want to draw it, well, you have to draw it. Because guess what, ladies and gentlemen? Electric field is a vector. So the direction matters. So, What does the aura look like? For a positive charge, the aura is going outside. Yes. The aura is pointing outside of the particle. Very good. But for a negative particle, the aura is pointing inside of the particle. Yes, yes, very good. Now, actually, fun fact, electric field is what causes uh, the force on top, right here. This electric field causes the force because if we place a random particle, it's gonna get pushed away by this field. Like if you put it, boom, it's gonna get, yeah. If you wanna think of it like this, I would like to add that a positive, an added positive charge will follow, but a negative one will rebel. It will not go the direction it's supposed to. What do I mean? Let's see. Here's what I mean. Positive, it's gonna point outwards, right? It's gonna point outwards. We know that. 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 It's gonna point outwards. Now we put another positive charge. It's gonna follow the arrow. It's gonna follow the arrow. It's gonna go there. It's gonna follow there. It's gonna go outside. But if we put a negative charge, oh no no no! It's gonna rebel. It's gonna go the other direction. I'm not gonna follow the arrows. I'm gonna break the rules. It's gonna go there. It's gonna go the opposite direction. And it's the same for this thing. This is pointing inside, inside. We know that, 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 we know that. If you have a positive charge, it's positive, so happy. I'm gonna follow the rules all the time. It's gonna follow the arrows. But if we have a negative charge, oh no no no. We don't talk about the negative charge. It's gonna go away. I'm not gonna follow the arrows, I'm gonna boom. And if you look at this is actually pretty damn accurate. Positive and positive, it's the same, so it's gonna repel. Positive and negative, it's different, so it's gonna attract. Negative and positive, it's different, so it's gonna attack. Attract. Negative and negative, they're the same, they're gonna repel. Wow, very cool. Now, how do we calculate the magnitude of the electric field? Well, the electric field is equal to K Q over R squared. What is Q? Q is the charge of this main particle, the aura final boss. That's it. Yeah, yeah. But you think about it. Wait, hold on. Hold on. This is F. It's pretty damn similar. And yeah, it's really similar. And from now on, I'm gonna rewrite F as capital Q and underscore under capital uppercase lowercase q. And if you look at this, wait a minute. F will equal to E multiplied by Q. Oh, so that's another way to find the force. How would we do that? Let's think about this one very quick. How do you find the force? So first, we're gonna find the electric field caused by the main aura boss, and if we put an a chud, an orofarming chud. What am I doing? With the orofarming chud, with the yeah, this is gonna have an electric field, and then this charge will experience a force caused by the electric field, and that force will equal to the electric field by the final boss multiplied by the charge of the chud. If you want to modernize and use slang. And yeah, that's basically it on electric charges. Wait, no, electric charges, electric fields. Very good, very nice. Wow, it's incredible. I want to talk about it more, but there's still so much to talk about. I'm so sad. Fear not. Let's talk about it anyway. Well, I mean, the strategy to solve electric field problems is actually really similar to force problems. But guess what? You only need one this time. Boom, boom. And then you have an imaginary point. Imagine you are here. And then the question is like, how much aura do you feel? uh, how much aura do you feel? 1 billion. Amazing. But yeah, it's basically problem solving for the electric field is actually really similar to the forces. But in forces, there's two charges. In electric fields, there's only, well, there could be more. But instead of analyzing a charge, you're analyzing a point and how much electric field does that point experience. And remember vectors. Please remember the vectors. Please remember the vectors. Please remember the vectors. So yeah, let's a simple overview. Boom, boom. Let's say here, boom. Let's say this is 3. Let's say this is 4, which makes this 5. What is how much aura? How much aura do you feel? This is negative, so it's gonna pull. Boom. This is positive, so it's gonna push. Boom. And there's gonna be an angle here, and then resultant of a vector. Resultant of a vector e squared e1 squared e2 squared plus 2 e1 e2 cosine theta. Boom, boom. But remember, cosine theta has to be like this. Boom, boom, boom. This is theta. This is not theta. This is theta. Very nice. Yeah, that's how you do. That's how you do the electric field problems. Yeah? Ih, baik banget. Thank you. Thank you. Iya, nak. Yo, monggo. Pentungan ayam. One that. It's okay. Quinchana. Ding, 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 ding. Okay. I'm gonna speedrun now. Guess what, ladies and gentlemen? There's still so much more. I already talked about that. Already talked about that. Flux? Do we need to talk about flux? Let's talk about flux really quick. Flux. Bro, I regret talking about forces this much. Why did we talk about force this much? Yeah, guys, I'm so sorry. I'm gonna stop talking about the force that much. Flux. What is flux? How much aura in a plane, or passing through a plane, basically. How much aura is there? So imagine, boom, this is a plane, and then the aura is like piercing through it. Bam, 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 bam. That's the flux, and the amount is defined as the how powerful the aura is multiplied by the area. This is the area of the plane. Very good, very nice. But remember, the direction matters. So if we have an aura pointing like this, oh, we don't want that. What we want is an aura. I'm gonna stop talking about aura. What we want is an electric field that is perpendicular with the plane. So we want something that looks like this. Ah, how do you do that? Imagine this is theta. And properties of a vector, this will equal to e cosine theta. So the final equation will look like e divided by a multiplied by cosine theta. Yes. Very nice. That's flux. That's flux. We just talked about flux. Alright? Okay. Cool. Let us continue. What do we continue now? Okay, parallel plates. Where did this equation come from? I have no idea. Okay, what about the aura? What about the aura of a plate? How much aura does a plate have? It's this. Where did this equation come from? Oh dear God. Judgment Day. No, it's not. I'm joking. I think that's part one. Will there be a part two? Yeah. If I learn how to pause this recording, I think there will be a part two. I don't know how to pause the recording though. Yeah, I think that button just stops the recording. Let's see. Screen record. I want to pause, please. Thank you. No clue to pause. Alright, we're gonna wait for the azan. I think it's done. Okay. Let's talk about this now. Basically, first I'm gonna define. Flux is also, according to Gauss, it's proportional to the charges in the enclosed space divided by epsilon naught emissivity, which is equals to 8.85 times 10 to the power of negative 12. Whoa, what a cool number that is. Okay, that's null by the way. That's null by the way. Yes. Oh my god, the chair needs to stop squeaking. I hate squeakers. Okay, so now I think Gauss, did Gauss do this? I'm gonna say Gauss. No, I'm gonna say me. I want you guys to imagine a plane. And this plane is currently being intersected by a sphere. Oh no. Now, there will be three parts of, well, three faces that we want to analyze. This is the plane, side view. This is the tube. This is the tube. This is the tube. I want you to analyze this one. Let's call it A1. This one, let's call it A2. And this one, let's call it A3. Now, oh dear God. Okay. Now this plane has some charges, and because it has charges, it has aura. It has E. So the E will point outwards from this one, outwards from this one, and it will point like towards the direction of this one. Let's call it that way. So if we look at the flux, the total flux of this star cylinder will be from the first one, the second one, and the third one, right? And the first one, the first one will be equals to E multiplied by A1, and this is, well, this is already perpendicular, so it's fine. And the second will be E multiplied by A2 multiplied by cosine of 90, because this is not even close to being perpendicular. If we want to make it perpendicular, we have to multiply it by cosine of this angle, which is 90, and plus EA3, which is already perpendicular, so that's fine. So we get EA1 plus EA3. This turns to 0 because cosine 90 is 0. Yes. And we need to remember that A1 is equal to A3. So the total flux will equal to 2EA. Alright. And then remember, phi is equals to the charges in an enclosed space divided by the emissivity. Yeah. And I want to define something. I want to define this thing. Sigma. This defines how many charges in one area. This is the charge density, I believe. And it's defined as the amount of charge divided by the area. The area. So we can get that the Q, the charges, is equal to the sigma multiplied by 8. And we know that phi is equals to that charge divided by E naught. So it's going to equals to epsilon A over E naught. That's... Oh, calculator, hello. Bro, we have to go down again? Bro, my god. Bromine. Honey, see you. Okay. Epsilon. Null. And remember, this is equal to 2EA. 2EA. Cross out the A's, and we'll get 2E is equals to sigma. Epsilon naught. Well, so much oral forming today, so we'll get E, solve for E. Electric field divided by 2 epsilon naught. Oh, very nice. We got it. That is from a plate. But what if we have two plates? Oh, let's say this plate is positive. You can barely see the positive sign, bruh. Oh my god. And let's say this plate is negative. Oh, negative charge. Now, let's just look from the horizontal side. I don't want to look at the angles. Negative side will point this way. And positive side will point that way. That way. Whoa. But then again, this area on the left here will experience some stuff from here, which is pointing inside. Oh, and this area here will be experiencing aura from this thing, which is pointing outside. So this is gonna cancel each other out, and this is gonna cancel each other out. Alright? Right. So between two parallel plates, the electric field is equal to 0. But here, they add up. So here, E is equals to what? This. Plus it again. So we'll get the electric field between two parallel plates is equal to sigma over epsilon naught. Let me check. Am I right? Am I correct? Yes. God bless. Very nice. Very cool too. Oh my god. Am I tired? Oh yes, I am quite tired, I must admit. Anyway, let us continue to the second object. We talked about parallel plates, but now let's talk about spheres. Sphere. Oh, that's a really big sphere. Okay. Now it's okay. Sphere. Now, we have a sphere. Okay, cool. According to my teacher, God bless my teacher. Hold on, the notes here. In a charged sphere, all the charges get pushed to the edge due to the repulsion force. Therefore, there are no electric field inside. So all of the charges will be here on the outer layer. Meanwhile, the inner layer here, no, nothing. There's nothing. There's nothing in the inner layer. Sorry. So, what is the aura? The aura by the sphere. Oh, hold on, wait. I'm gonna do something really fancy. Boom. So imagine we have a sphere. Let's make it smaller now. Now remember, it's all on the outside. We're on the edge. Nothing on the inside. So I'm gonna draw a diagram now. The y-axis determines the size of V, and then here R, the radius of the circle. It's gonna look like this. Oh, very cool. What does that mean? What does that mean? That means the electric field of the inner circle, like the inside, is equals to 0. But once we get to the edge and outside of the circle, is basically equals to kq over r squared. Q is the charge of the circle. But another equation we have is it's equal to q over 4 pi r squared epsilon no. How do we get that? How the freak did we get that? This is how. Remember Gauss law? EA to Q in epsilon naught. So E will equal to Q over A epsilon naught. What is the surface area of a circle? Oh wait, 4 pi r squared epsilon naught. Wow. Yeah, that's how you get it. But then again, you might be thinking, wait, hold on. I'm seeing some similarities. If this is the same, does that mean K is equals to 1 over 4 pi epsilon naught? Yeah. Anyway, that is the electric field. Ladies and gentlemen, let's move on now. I really want to get this over with. I haven't eaten. I am hungry. The man is hungry. Let us continue to electric potential. What is an electric potential? I don't know, honestly. I want to say it's aura, but it's not really aura, but electric potential or volts. Let's look at the book. Electric potential is defined as the potential electric energy of a test charge divided by one test charge. Wait, what? Oh, it's defined as the potential energy of the electrical potential energy of a test charge for every one test charge. What? Oh, so we have to talk about potential energy first. Okay. Awkward. Electric potential energy. Yay. Now, well, I mean, I think we can do some calculus here. Okay, I'm just gonna derive the equation really quick. Let's see. Boom. Let's say it's gonna boom by boom. Let's say this is R1. This is R2. Boom, 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 boom. R1, R2. R1, R2, K, Q, Q, R squared, the R, negative K, Q, Q. I forgot. Wait. So the power gets added, and then it becomes the multiplier. So this, um, Yeah, this becomes negative 1 multiplied by 1 over r. Limits of r1, r2. This gets crossed out, so this becomes k q of 1 over 2 minus 1 over r1. Nice! Or EP is equals to k q over r. Yes, sir! Very similar to F, if you may see. But if we multiply by R, then we'll get it. So F multiplied by R is equals to EP. Very EP? It's in joules. I'm very EP. Okay. What is an potential energy? We've seen it in energies. Come on. Must I explain energy? Honestly, I can't. Yeah, anyway. Alright, now on to volts. Volts. It was potential energy of a test charge divided by that test charge. So that's... I did not... Whoa, what the frick? You see that title? That's insane. Anyway. Boom, 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 boom. Go, 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 go. And then this Q. Cross that out. So KQR. Okay. Okay. Yeah, that's it. Do I know what this is now? Okay. Yeah. Cool. It's still the same. R is still the distance between two charges or 2 points. Yeah. Oh wait, but I do need to mention electric potential. Hold on. Electric potential energy and electric potential or volts. These are scalars. They are. I did not mean to close that. But okay. I see how it is. I see how it is, my good man. Okay, I see how it is. I see how it is. These are what the freak? Scalars. So direction does not matter. However, I do need to mention in scalars. Bring the negative. Bring negative. In vectors. That's not. Don't bring negative. What do I mean? What I mean is that in scalars, if we have a charge that is like -2, we're gonna bring that negative number into the equation. But in vectors, if I have -2, I don't bring the -2, I just bring 2 into the equation. Okay? Let's recap everything. We have F equals to K Q R squared, E, which is equals to KQ R squared. We have V, which is equals to KQR, and we have EP, KQQR. We can bridge them. Whoa, this is a really cool diagram I saw on my teacher's presentation. So F is equals to E multiplied by Q. V is equals to E multiplied by R. V multiplied by Q is equals to EP. And EP is equals to F multiplied by R. Nice! Let me check everything. E multiplied by Q, that's F, yes. E multiplied by R is V, yes. V multiplied by Q, that's EV, yes. Very nice. What is next upon the notes? Potential of a ball. Interesting. Oh, yeah, yeah, yeah. Okay. So imagine we have a ball. Again, remember the inside is equals to 0. So the difference of electric potential is equals to 0. Which means if we have an electric potential here, it's gonna be the same here. If I want to draw the graph again, we'll get this. Boom boom, boom boom, boom boom, boop, and then it starts to get down because of distance. So yeah, V is equals to K, Q, R, where R is the radius of the circle. If R turns out to be smaller than the radius of the circle, let's say here, don't plug in that number. Plug in this number instead. Because inside of the circle, it has the same voltage as outside of the circle. Not different. Yes. Now plates. Oh, talking about plates again. See. Plus. Negative. The voltage is equals to what? The work needed to move from point 1 to point 2 is equals to Q multiplied by the difference in the voltage. And we also know that the work done is equals to F multiplied by D. So F multiplied by D is equals to Q multiplied by V. And we know then we know F is equals to Q multiplied by E. So I'll get Q multiplied by E multiplied by D is equals to Q by V. So I'll get ED is equals to V. Oh. Yeah? Okay. Boleh banget. Nah, this is the distance. Aku keluar dulu bentar ya. Siap laksanakan. Okay. Cool. Very nice. Where's the bridge? There's the bridge. There's the bridge. V is multiplied by E multiplied by R. Well, not R, but just the distance. Oh, capacitors. God, I'm speedrunning. I'm absolutely speedrunning capacitors. Capacitors, basically batteries. I want to be so done with this. Oh my god. I was so motivated in the beginning, but now I'm tired. Capacitors. Basically, batteries. They're stuff that can store not potential charges. Yes. Why? How? So we have two was it conductors, and then there's like an isolator here. And if we hook it up to a battery, the charges are gonna move, making this positive and making this negative. And then if we cut that circuit, the charges will stay the same. Very nice. Basically a battery. Basically a TLDR, a battery. Very cool. Very nice. The capacitor or the capacitance of a capacitor is defined as Q multiplied by V, where V is the voltage of the battery right here and Q is the amount of charge stored inside of that capacitor. The unit is Farad. This is my favorite unit. CF. C is Farad, yes. So yeah, this is the equation. C is equal to Q. Excuse me. Whoa. Over V. But what if we only know the area of this plate and the distance between them? How do you do that? Well, remember that the electric field of a plate is equals to the Q. What the freak is that? Yo, okay. There we go. And we also know that E VD. Q A E null V D. Q, bro. You gotta be kidding me. We're going down. I see you running downtown with the girl I know, and I'm like, freak you. Let's go. We're almost there. Let's go. I'm almost done with this. Is this a good video? I hate this video. I'm gonna be honest, guys. I'm gonna put a TLDR on the title. TLDR. Sick man tries to teach physics, does not end well. Q. VA. Enol. D. Oh. C. VA. Enol D. Wait. Enol D. V. C. Enol AD. Yes, that's what we do if we only know the area of the plate and the distance between the plates. That's what we do. That's what we do. But here's the problem. What happens if, because this thing determined by epsilon null, and as far as we know, epsilon null is a constant. Well, guess what, baby? No. Well, yeah, it is a constant, but it only it's dependent to the material that is put here. Like, what is here? What is there? What? So, if the stuff here is not associated to epsilon null, then the answer is going to be different. So, a function of it, the difference in material, it's going to be multiplied by constant, A over D. What is this constant? This constant is the book, the dielectric constant, where the constant is defined as the emissivity divided by emissivity of air. Oh yeah, this is for the material we're using, and this is, yeah, it's gonna cross out. Yeah. Basically, it depends on air. Remember, it's not always epsilon null. Yeah. Oh my god, we're almost done. Oh my god, we're almost done. Yes. Capacitors. This is the symbol for a capacitor. Two parallel lines. Very nice. Okay. What happens if we put capacitors in series? Well, first let's think about it. The Q, or the charges stored here, is gonna be the same. So the Q total equals to the Q stored in this one, L equals to Q stored on this one, and the V, guess what, baby? It's different, but it's gonna add up to the same. This is the, I think it's Kirchhoff's second law. Yeah, basically it's gonna be the sum. What about the capacity? Well, let's remember. C QV. I see. V QC. I see. So Q total, C total, Q1 V1, Q2 V2. But oh wait, it's the same. Wait, why is it V? It's supposed to be C. Oopsies. C1, C2. So we get the total capacity of a capacitor in the series is equals to 1 over C equals to 1 over C1 plus 1 over C2. But what about in parallel? Oh, what about in parallel? Truly, question of the year. Let's go ahead. Same potential, okay. Why is it the same potential? Frankly, I don't know. And then the Q's become the total. It gets add up. And then remember, CTVT, C1V1 plus C2V2V is the same across the mouth, so we'll get CT is equals to C1 plus C2. So in parallel, just add them up. Very cool, very nice. And the energy stored in one of these things is equals to Yeah, I'm tired. My brain is totally fried. Oh my goodness, someone help me. And that is all of the materials. I would like to formally apologize for half-assing all of these materials. Because guess what, man? I'm tired, I'm hungry, and I'm really thirsty. I already drank though. I lied, I'm not thirsty. I'm just tired. Okay, let's continue. 2D practice questions. We already did number 1, we already did number 2, we already did number 3. We already have we done number 4? I'm gonna do the practice questions. Number 4. Same side triangle. Distance is 30 centimeters. Boom, boom, boom. 2 microcoulombs, negative 2 microcoulombs, 2 microcoulombs, and 3 microcoulombs. Wait, this is A, this is B, this is C. What is the total force on C? Let's draw it. This is C, and this is negative. This is negative, this is positive, this is positive. So negative will pull it, and positive will push it. So go boom, boom. What is this angle equal to? Well, if we do this, you know that this is 60. So this will theta will equal to 180 minus 60, which is equals to 120. Right? Let's just keep that in mind. And this is FCA. This is FCB. FCA is equals to KQCQA R squared. R is the same for both. 9 times 10 to the power of 9 multiplied by QC is 3 multiplied by 10 to the power of negative 6. QA is equals to 2 multiplied by 10 to the power of negative 6 divided by R squared. R squared 0.9. Wait, no. Wait. 0.3 multiplied by 0.3. That's 9 times 10 to the power of negative 2. Boom, 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 boom. Okay. Boom, boom, boom. Boom, 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 boom. Boom, 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 boom. Boom, 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 boom. Boom, 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 boom. Boom, 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 boom. Is that the same? Oh, it is. Nice. Oh, it's not 12, 6. Just boom, 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 boom. Boom 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 boom. Cosine 120 180. Boom 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 boom. Hey, I just said boom for like 6 minutes in a row. Okay, you guys know what that means? That's a sign. That means I'm hella tired. And there's absolutely no use for me to continue this video because guess what? The people watching this will get absolutely zero benefit from watching this video because guess what? It's all just booms for 20 minutes in a row. There's barely any explanations. I hate this video. If I can delete it, I will. But guess what? I can't. So I'm not gonna delete this video. I'm gonna upload it anyway. Thank you for watching. I'm still alive. Just forgot the channel existed. Will I be uploading more? Probably not. Uh, although I'm planning to upload a kinematics video. Yeah. Stay tuned for that. Yeah. Thanks. I'm gonna eat now.